This is the Daily Space for today, Tuesday, November 17th, 2020. I am your host, Dr. Pamela Gay,
And I am your host, Beth Johnson.
and we are here to put science in your brain. Today's news allows both Beth and I to go down the rabbit hole with our favorite parts of science. For me, this means looking at the weird and wonderful history of our galaxy and all the ways it finds to try and kill us. This is a bit dark, perhaps, but as a Gen X kid hitting middle age in 2020, it somehow feels appropriate. For instance, let's look at our own shining Milky Way galaxy. From a dark site, a nice lawn chair, for instance, with a good pair of binoculars, you can explore our sky and take in globular cluster after globular cluster in all their star puff glory. These splats of light on the sky contain tens to hundreds of thousands of stars that are readily studied and that consist of old and, well, metal-poor systems that we don't see locally. Early on, it was realized that globular clusters come in distinct populations that differ in direction of motion around the galaxy and in chemical composition. These are the original Oosterhoff type 1 and type 2 globular clusters that first led people to ask, did some of these star clusters come from cannibalized galaxies? Over the decades, our abilities to measure composition and motion have improved, and our ability to model what kinds of interactions build up what kinds of different galaxies have also progressively improved as our computers have gotten more powerful. Today, researchers have the ability to look at the Milky Way and its more than 150 globular clusters and run back the history of our galaxy using these simulations. And we're able to figure out what kind of a merger history is required to get us all the things that we see. Now, massive galaxies form in two ways. Early in the universe, they formed through the wholesale collapse of massive clouds of gas that caused things to go from zero to galaxy in a single epoch. Since then, galaxies have formed piecemeal, with small systems collapsing from clouds of material early in the universe and then coming together and building massive galaxies up, well, merger after merger over time. And in the subsequent 10 plus some odd billion years of galaxy mergers that have taken place, our own Milky Way has grown through continued cannibalism of smaller galaxies. Now, while we're able to see this ongoing galaxy cannibalism, what we hadn't been able to do until now was figure out exactly how many significant merger events occurred in our galaxy's past. Now that has changed. An international team of researchers has published a study in the monthly notices of the Royal Astronomical Society with lead author Diederik Kruijswijn. And this study shows that at least 5 major mergers were needed to build our Milky Way. And these mergers have names like the Gaia Enceladus merger, after a sausage-shaped distribution of stars that has been observed, the Helmi streams, the Sequoia stream, the Sagittarius stream. And according to Kruijswijn, the major challenge of connecting the properties of globular clusters to the merger history of their host galaxy has always been that galaxy assembly is an extremely messy process, during which the orbits of the globular clusters are completely reshuffled. To make sense of the complex system that is left today, we therefore decided to use artificial intelligence. We trained an artificial neural network on the eMosaic simulations to relate the globular cluster properties to the host galaxy merger history. We tested the algorithm tens of thousands of times on the simulations. These were simulations of different galaxies, and were amazed at how accurately it was able to reconstruct the merger histories of the simulated galaxies using only their globular cluster populations. Now, what amazed me the most about this research is they not only recovered events we'd already understood, such as the merger with what has been called the Gaia Enceladus sausage galaxy that took place about 9 billion years ago, they also discovered a previously unknown population of stars that indicated a previously unknown collision that took place 11 billion years ago. Now, this research is based on globular cluster measurements. And as Gaia and future survey scopes measure the galaxy's stellar population, there is hope that we should be able to find stellar populations tied to all 5 of these systems. Now, I named 4 of these systems. That 5th system, that 5th merger they just discovered, well, this monster collision is now thought to be the latest merger and to be the largest merger that has taken place, and it has been given the name the Kraken. And this is one of the few examples I know of where scientists really should be allowed to name things.
While Pamela is delving into the weirdness of our galaxy, I'm over here trying to find life. Most of you know that at my other job, I work at the SETI Institute, so astrobiology is always on my mind, which brings me to my first story. For decades, scientists have been curious about the plumes of water vapor erupting from the Jovian moon Europa. Analysis of Voyager data, Galileo data, and even Hubble data has led scientists to think that Europa has an icy shell 15 to 25 kilometers thick, floating on an ocean 60 to 150 kilometers deep. In recent years, astrobiologists have looked to that subsurface ocean as a potential habitat for life. The hope is to sample the vapor someday soon using the upcoming Europa Clipper mission and find evidence of biology. However, new research published in Geophysical Research Letters has produced a model of the eruptions that shows they come from brine pockets near the surface rather than deep underground. The researchers used Galileo data of an 18-mile wide crater on Europa called Magnetar to show that a combination of freezing and pressurization could lead to a cryovolcanic eruption or a burst of frigid water. If the plumes originate in the icy shell, they likely won't carry any components that provide the possibility of life. However, if the plumes come from deep cryovolcanoes, they could harbor life, similar to the way underwater thermal vents do here on Earth. The results of this model aren't good for astrobiologists, unfortunately. The crater is the result of a large impact that occurred millions of years ago, and that impact would have generated tremendous amounts of heat. This new model proposes that the impact melted the surface ice and brought water up from the ocean. Then the subsequent freezing of the liquid water created a pocket within the icy shell. That pocket then became pressurized and eventually caused water to erupt. Fascinatingly, the model also shows that these pockets of water, which contain more brine than the subsurface ocean due to mixing with the material from the impacts, can actually move sideways under the ice. In the case of Magnetar crater, a pocket moved, and when it reached the shallower center of the crater, the pressure from the surface ice decreased substantially, and whoosh, eruption. There is good news here for both astrobiologists and planetary scientists. Per the press release, the relatively small size of the plume that would form at Magnetar indicates that impact craters probably can't explain the source of other larger plumes on Europa that have been hypothesized based on data from Galileo and NASA's Hubble telescope. But the process modeled for the Magnetar eruption could happen on other icy bodies, even without an impact event. So while this particular research doesn't get us closer to finding life, it doesn't entirely preclude it either.
Now, while life is exciting, you have to know how to make stars before you can know how to make planets. And folks, not all stars can make planets. Stars that lack the complex elements found in our sun, Metalpoor stars, to use the terms of astronomy, they aren't associated with the chemistry needed to build worlds. They are instead galaxy builders and the siblings of the stars that exploded and created the elements that went into making solar systems like ours. Now, for the past 20 years, astronomers have been searching our galaxy for the oldest and the most metal poor, most chemically boring stars that are out there. Because small stars can live essentially for longer than the age of our current universe, there's reason to think that some of the second generation of stars are out there still shining in our sky. And by finding them, we can find essentially trace particles of all the systems that merged in to, as was discussed in my first story, form our Milky Way galaxy. Now, in that first story, we looked at the globular clusters and used them to figure out the merger history. Well, we can also look at the stars, but that's a bit more imprecise because we're limited by what we can see by all the dust and galaxy within, by all of the dust and gas within the galaxy that limits how far we can see across the disk. We can see above, we can see below, we can see a little way through. But we can't get that same holistic picture that we can get by looking at the globular clusters that form a sphere around the Milky Way. Now, all because something's hard doesn't mean we don't try and do it. And in a new study published in the monthly notices of the Royal Astronomical Society, with lead author Giacomo Cordani, the orbits of 475 metal-poor stars have been described. These are stars that have 1,000 times less iron than our sun, stars that probably can't support any planets. And what was amazing looking at these stars is they come in orbits that seem to fall into several broad patterns. They were able to trace out the populations of that sausage and sequoia merger that came up earlier. And they were able to see other populations largely in the outskirts of our galaxy or diving through the plane of our galaxy on their way, just passing through on a larger orbit. But mixed in with all of these stars that, well, like to spend most of their time out in the spheroid of the galaxy, were also 50 stars on nice normal orbits going around the center of our galaxy and staying confined to that disk of our galaxy. Um, these aren't stars that we expected. They probably came here via mergers and found their way from larger orbits that carried them out to the spheroid of the galaxy into their present orbits through, well, that is for future research. But what's cool is now we know that there are these different populations of metal-poor stars that we have to be able to explain. So as we work using globular clusters and software and, well, every means at our disposal to figure out the history of mergers that led to our Milky Way galaxy, we now have to also explain not just how those globular clusters got into all the different orbits they're in, but also how individual stars can make their way into the plane of our galaxy over time. We don't know. This just we know will inform future models.
My next story made me smile so wide last night that I hurt my jaw. University of Santa Cruz professor and exoplanet expert Dr. Natalie Battaglia has been tasked by the NASA astrobiology program to lead a newly formed interdisciplinary consortium that will trace volatile elements in planetary atmospheres. These elements could become the key to finding signatures of life on exoplanets. The consortium was awarded a 5-year, $5 million grant to do the work. As Dr. Battaglia said, we want to understand the physical processes that impact planetary atmospheres. We must understand these physical processes and their effects in the absence of life so that we will be able to recognize the signs of life when we see them. Dr. Battaglia, who was previously the project scientist for the Kepler mission, goes on to note, One of the takeaways from the Kepler mission is that the diversity of exoplanets in the galaxy far exceeds the diversity of our own solar system. If we want to understand the diversity of rocky habitable zone planets, we have to study the physical processes that sculpt the atmospheres of all planets, even those not amenable to life as we know it. The team aims to follow volatiles like carbon and oxygen from star forming clouds into protoplanetary disks to the building blocks of planets and eventually into planets themselves. Per the press release, the researchers will address four fundamental science questions. What is the inventory of volatiles in planetary building blocks? What are a planet's external sources and sinks of volatiles? In other words, where do they come from and where do they go? How are volatiles distributed between a planet's interior, surface, and atmosphere? And what can atmospheric observations tell us about the volatile inventories and chemistries of exoplanets? The team currently consists of members from the University of Hawaii, the University of Colorado Boulder, the University of Kansas, as well as UC Santa Cruz, and they will utilize a host of scientific equipment, including the Atacama Large Millimeter Submillimeter Array, Hubble Telescope, various ground based telescopes, and maybe one day the JWST. I am definitely looking forward to seeing where this research goes.
Now, as often happens in science, things are a cycle with one study building and expanding on another. And today we have research that builds on a story we presented just last week. And this is because researchers talk to each other well before the publications necessarily hit the page of your local journal. In this case, we have an update on the Magnetar SGR 1935 plus 2154 that we talked about last week that was associated with a event that appeared to be a fairly low power fast radio burst. Fast radio bursts are events that last less than 2 seconds and give off in that amount of time massive amounts of energy that were initially thought to be glitches in the system when they were detected by radio telescopes. But now we've been able to identify systems where these radio bursts appear for periods of time randomly, then shut off, then come back in the same direction in the sky, indicating that there are objects out there that turn on and turn off over time. Exactly what's going on, we're not sure. But when we see this kind of a turn on, turn off behavior, when we see these kinds of massive energetic outbursts, well, we've learned over time to recognize there's probably a compact object, some small, extremely dense, high gravity source that is doing something probably to a neighbor or to itself, maybe. And now we come to understand that what is probably happening with these fast radio bursts is the magnetic field lines in these systems, driven by starquakes and other events, are releasing massive amounts of energy. And it's that massive amount of energy that we see as these fast radio bursts. Now, this harkens back to last week's research where we saw a single massive event that occurred on SGR 1935 plus 2154 after it had been active in the X-rays for some time. Well, because we know there are repeating fast radio bursts out in the distant galaxy, or rather out in the distant universe, it was hoped that this little magnetar might also repeat its energetic adventures. And in a new paper appearing in Nature Astronomy with first author Franz Christen, it has been revealed that just such a massive outburst occurred. It still wasn't massive enough to equal what we see coming from magnetars in other galaxies, but these are rare events for the most part. But they monitored this system with a series of radio telescopes around the world, around the clock, to make sure that any short burst that occurred would be captured. And on the night of May 24th, according to the press release, the team got the surprise they were looking for. At 23:19 local time, the Westerbork telescope in the Netherlands, the only one in the consortium that was on duty at that point, it caught the dramatic and unexpected signal of two short bursts, each 1 millisecond long, but 1.4 seconds apart. It works, folks. Magnetars appear to be the source of, well, fast radio bursts. And we're just going to keep watching and documenting what is going on in these crazy, dense, highly active systems scattered throughout the universe.
Back to the search for life and its origin. Glycine is the simplest of the amino acids, and it has commonly been thought to require energy to form. However, new research, also published in Nature Astronomy, looked at recent findings of glycine in the coma of Comet 67P and in samples returned to Earth by the Stardust mission. Comets are considered to be pristine examples of material that existed during the beginnings of our solar system. And so this discovery means that glycine is produced long before stars form. This new research shows that it is possible for glycine to form on the surface of icy dust grains through, I love this term, dark chemistry, which contradicts previous studies that suggested UV radiation was required. Lead author Dr. Sergio Iapolo said, "Dark chemistry refers to chemistry without the need of energetic radiation. In the laboratory, we were able to simulate the conditions in dark interstellar clouds where cold dust particles are covered by thin layers of ice and subsequently processed by impacting atoms, causing precursor species to fragment and reactive intermediates to recombine." Chemistry words. Harold Linnertz, director of the Laboratory for Astrophysics at Leiden Observatory, goes on to explain. This important conclusion from this work is that molecules that are considered building blocks of life already form at a stage that is well before the start of star and planet formation. Such an early formation of glycine in the evolution of star-forming regions implies that this amino acid can be formed more ubiquitously in space and is preserved in the bulk of ice before inclusion in comets and planetesimals that make up the material from which planets are ultimately made. The formation of glycine opens the door for the formation of more complex amino acids, such as alanine and serine, in dark clouds in space. All of these organic molecules are now thought to be included in early celestial bodies, like comets, and subsequently delivered to rocky planets like Earth, spreading the potential for life.
Now, we've talked a lot about creating life, but at the beginning of this episode, I promised death and destruction. And while magnetars do have the potential to release the kinds of energy that can destroy things, maybe even kill things, I want something bigger. So let's consider some supernovae. Researchers have been looking at the history of the radiocarbon element carbon 14 and looking to see if it can be linked to events where supernovae may have affected our planet. Carbon 14 is a short lived, relative to the age of the universe, radioactive atom that decays. And it's formed on a regular basis by cosmic rays impacting our planet's atmosphere and in the process changing one kind of element into another, generating the carbon 14. Now, life likes to pick the carbon 14 up and embed it in our bodies. And life doesn't just form flesh sacs like human beings, it also forms trees and other kinds of extremely long lived things. But here it's the trees that we're most interested in. It turns out that, well, trees live for a really long time and then have this convenient habit of doing things like fossilizing nicely and otherwise just, well, leaving behind beautiful tree ring records of their past. And it turns out that You can look through these tree ring records for carbon-14 levels. And according to a press release on new research published in the International Journal of Astrobiology by Robert Breckenridge, it looks like the 8 closest supernovas studied all seem to be associated with unexplained spikes in the radiocarbon record on Earth. He considers, according to the press release, 4 of these to be especially promising candidates for forming the radiocarbon atoms, that carbon-14. Take the case of the former star in the Vela constellation. This celestial body, which once sat about 815 light years from Earth, went supernova roughly 13,000 years ago. Not long after that, radiocarbon levels jumped up by nearly 3% on Earth, a staggering increase. What they think is happening is supernovae go off not too far away, distances consistent with where we think Betelgeuse is. The cosmic rays from these supernovae then affect our planet, triggering the creation of carbon-14 that then appears in the fossil record. And may also appear not just as tree rings, but also as die-offs of life on our planet. These are things to be considered. Perhaps by me with a little too much glee, because I love this kind of science where we figure out just exactly how the universe is trying to kill us. Now, when Betelgeuse goes, it'll probably be about 100,000 years from now, so we don't need to worry. But it's still cool to think that far in the future, a star will change the composition of life on our world. Wait, I goofed again. There, now go.
Finally, a heartfelt congratulations to the NASA SpaceX Crew 1 mission, which not only successfully launched over the weekend, but docked with the ISS last night. On board the Crew Dragon were NASA astronauts Michael Hopkins, Victor Glover, Shannon Walker, and Japanese Aerospace Exploration Agency astronaut Soichi Noguchi. Their special guest was none other than a plush Baby Yoda. Our colleague Annie Wilson will have full coverage of the launch tomorrow on Rocket Roundup, so please join her then. This has been The Daily Space.
Today's episode of The Daily Space was written by myself and by Beth Johnson. I am Dr. Pamela Gay. Engineering is provided by Ali Pelfrey, and web content is produced by Beth Johnson. You can get today, there won't be a complete transcript, no lies. Today's episode was brought to you the day after a major grant deadline for the National Science Foundation. And we pulled together this science after spending a lot of hours trying to get funding for our own future science. So you can find show notes and see images related to each of our stories at our website, dailyspace.org. We are a production of the Planetary Science Institute, a 501c3 nonprofit dedicated to exploring our solar system and beyond. This show and all of the science communications efforts that we do here at CosmoQuest are brought to you by you. We can only get so much funding from the government to do so many different things, and that funding goes to us generating new science, to us inviting you to join us in our citizen science endeavors. If you want to learn, well, unfortunately, we have to ask you to help provide the funding for that. If you are doing okay in these plague times of 2020 and you have something to give, well, Giving Tuesday is next week. Please consider donating. Please consider becoming part of our Patreon family. Learn more at patreon.com/CosmoQuestX. Thanks.